what I'm going to do is
Wait a
actually.
second.
Yeah, the. Okay. So, is it okay? Can you hear me?
Maybe you can put the thing a bit higher up.
Okay. So what I want to talk about is actually two problems where one is in the context of crystalline phase transitions and one is in the context of viscoelasticity, where we've been using ideas of kinetic theory to study certain problems. And the first problem, actually, kinetic theory is not salient to that. Let me present it first. It's a one-dimensional model. You cannot really generalize this two dimensions, but I want to show you what it is, because both of them, they are actually diffusion theories of some sort. So what we will have here is a system of ordinary differential equations, which will be of this form, that each of them describes the motion of line defects. So now the lines, they are steps, and inside them there are atoms that are moving, and the problem is one-dimensional. Well, the interest here is to present a couple of models and to present the macroscopic theory, which is well known, and also to see how you can approach that from the perspective of kinetic theory. Let me get into that into the models. So what we have is we have a monotonic surface which consists of steps, and this would be, let's say, the magnifying lens view of the surface. And we're interested in describing the relaxation of a surface to equilibrium surface below the roughening transition. And there are two types of processes that I want to describe. And one is the crystalline surface is in local equilibrium with its vapor phase, and the relaxation is affected by adsorption-desorption process. So you have atoms that are moving from the surface to the environment or back to the surface, and this is all that's happening. And in the second one, you have a crystal in vacuum. This is called evaporation condensation. The second one, you have a crystal in a vacuum, and you have atoms that are moving inside the surface, and they may hop on the upper side or the lower side. And you have reconstruction of bonds, and this process is called surface diffusion. And there is a continuum thermodynamics theory for these models, which started this area, and which are gradient flows, both of them. And it was developed by Spohn in '93. So in the evaporation condensation process, the model is that h is the height of the surface. Let me go back. So this is the height of the surface is moving with respect to the gradient, where the function gives you the elastic energy of a surface. And if you compute, you get some kind of second order differential equation in this case. For the surface diffusion process, the model is that you have conservation of mass for the surface height relative to a surface flux, and then the flux is moving by the gradient of the derivative of a functional, and this would give you a fourth order equation if you carry out the equations. This is all in situations that are stable. Of course, this kind of equations, they can describe Allen-Kahn and Kahn-Hilliard respectively. I'm not in this situation. I will be in situations where the functionals will be convex, etc. And the interest here is to see microscopic theories that go to these models. All right, so for the evaporation condensation, the theory that existed is the Burton-Cabrera-Frank theory that started, in a way, this area in the 50s. And what you have is you are assuming xi, remember, maybe let me go back to the original. So xi would be the position of the ith step, and it's given by an equation that I would like to tell you what is the discrete model. So in the evaporation condensation model, you have that, according to this theory, you have that xi dot is given by the difference of chemical potential of the vapor with the chemical potential of the ith step. And if you normalize things, it would be like minus mu I, where mu I is like a chemical potential, which is like a force, right? So the chemical potential will be given like the derivative of the total energy of the steps. And here I have recorded only two terms. Now, the steps here, and this is a feature of these problems, is that these problems are not of mean field type, but they are of nearest neighbors or next nearest neighbors type of form. And the only ones, the total energy would be the sum of all the energies of pairwise interactions between all the steps. Since you differentiate with respect to xi, there are only two that will enter here. And then the question is, what will be the energy that you have to select? And for some reason that I don't understand very well, you take elastic dipole interactions for this, which means that G looks like A over W to the cube. Okay, then if you introduce that here, what you get is you get this kind of model. So V, you take the derivative, so G would be the derivative of V, and you get this kind of equation. And now we are interested, and there is also the surface diffusion model, which let me not describe it here. It's far more complicated. Maybe I'll say something a little bit later, if there is time, which is actually the original interest of this, but it's much easier to talk about these models, and the mathematics is the same. So in any case, we take now this equation, and first of all, let me describe how they do the macroscopic limits for this case. So the macroscopic limit, the problem here is scaled appropriately, which means that you select some kind of time scale. And what you want is you want to look at the macroscopic description of that. And let me say how this is done. This is work that is well known in this area, well, there is really a lot of literature, and my co-author is an expert on this area. So let me explain how it's done, let's say, here. So you have the steps, and A, the parameter A is the height of this surface. And you assume that these steps, they form a certain surface, and that they arrange themselves. This theory, as far as physics goes, is completely rigorous, but as far as mathematics goes, there are assumptions that I will point out later. But let's say that the steps arrange themselves in a surface. Okay, if they do that, you will get this equation here. You can calculate the derivative of this equation, and therefore you will get that xi dot is given like the h sub t over the h sub x partial, which is okay. And mi would be is the slope of the surface, and it is the height over the difference between two consecutive steps. Okay, and this approaches the slope. Now, we go back to the ODEs here, and you see, if you view these ODEs as ODEs in this direction, then the step sizes they are different. So it is easier to think of them in terms of step sizes on this side, where the step sizes are the same, in order to do your calculations. So if you do that, we are going to introduce, this is the slope of the surface. And we rewrite 1 over a by introducing this difference at the slope, and then you see it's very clear what's going on. You get xi dot is minus ht over hx from the kinematic compatibility condition that we had in the previous slide. And then if the slope stabilizes, this will give you an x derivative of the slope together with the term. So this is, you get this parabolic differential equation given that g is what it is. It's decreasing here. Okay. So this is the way that you obtain the limit in this theory as it goes to 0. Now let me now try to visit this problem from the perspective of kinetic theory and see how this will work. So the feature of this problem is again that there are nearest neighbor interactions, and we are interested in computing the hierarchy that you would describe the kinetic description of this system of ODEs. What you do is you introduce the empirical measure here, which counts if at the position y, how many steps in the limit you are going to measure. How many xi's of t go to there. Then the function f2 describes the 2-point correlation functions. Now, because you have nearest neighbor interactions, you are going to correlate every step with the next one, so you are going to define it like that. And Fn will have n nearest neighbor interactions. Okay, so you define f2 of a like that, and Fn of a like that, and so on. Okay, and you compute what are the equations that f1, f2, and Fn of a satisfy. And this is a tedious computation, but it can be done.
Why do you just restrict to consecutive values of I for the particle correlation?
Because I have nearest neighbors interactions.
But you could correlate after.
Yeah, they correlate after several steps. So in 2 steps, you have for the 2-point correlation, they are only nearest neighbors. For 3, they are 3 and so on.
That you can delete the other terms.
Well, it's not, you know, you have to decide how to do it, and this is how I decided to do it. And then the problem closes eventually, you know. You can get equations that, okay, so let me say, actually, all right. So what we're going to do is I will show you the equation in a moment, but I want to get a handle of the microscopic description, and the main thing that we wanted to do is to compare these models with models containing mean field approximations. And okay, which are these ones here. Now, if you compute the equations that you have, you will see that in order to compute f1, this is the BBGKY hierarchy before passing to any limit. That f1 is computed in terms of f3 because you have 2 nearest neighbors. f2 will be again computed in terms of the nearest neighbors, so they will go x, y, z, and then on the other side from y, the points. And this is the general form. So for Fn, you will need Fn plus 1, starting from 1 point to the left and going all the way up to 1 point to the right. So you get this kind of system, and actually, after we got that, we were puzzled. We were trying to understand what is going on. And if you compare it with what happens with the mean field approximations for the McKean model here, which was analyzed by Pulverendi, you see that this one actually closes like the Boltzmann equation. Namely, there is a propagation of chaos assumption, and if you do that, you can obtain an equation for that. And here it was not possible to see that. So what we did is we tried directly to calculate the limit as a goes to 0. So let me show you how this is done. This actually can be done here. So So the issue is to understand what is the density function with respect to the picture, to the geometric picture we have here. And let's say if you calculate this integral between 2 points xa and xb, this integral, if you think of that as delta masses, there will be equal to the number of jumps in the surface that you have. So it will be of the form nb minus na times a, where nb is the position of the point xb and na will be the position of the point xa. So it will be like the difference of the heights. And that means that in the limit, f1a will be the function that will be the slope of the curve. And once you see that, for example, one feature that happens in these models is that although there are interactions between, let's say, the point I and, for instance, nearest neighbors, in the limit, these interactions decouple in the sense that the dominant term in the limit is the one that is sitting at the point I, and the next ones are small of 1 relative to the parameter a. That is the height here, the microscopic variable. A times n would be 1, right? The number of particles times a. So then you can prove the following thing, working directly with hierarchy, that if the function zi that is on the right has this kind of feature, is within leading order is v at the position xi plus small o of 1, then the limit you can compute, and it is given by this function. This is what f1 satisfies, and the nth order function would be satisfying this kind of equation here. So somehow in this problem, in the limit, the first equation is the one that matters, that you compute, and then the other equations will be the ones that will compute the correlations from the correlations of the initial data. This is how this kind of problem works. And then now we are in business, we can calculate. For instance, in the evaporation condensation, this is what V does. And then you plug that here, and you get a second order equation. So you see the way that you get a parabolic equation is in this way, from here. And then Fn is computed by this kind of formula, where this is V. And this solves also the problem of surface diffusion. Maybe, given the time, let me not go to the microscopic description of surface diffusion, but let me just go to the result. You get eventually an equation that is of this form, a system that is of this type, where mu I is of the previous form, right? It's again dipole interactions, but here you have a more, let's say, more neighbors to consider for each point of the interaction. And then what we do here is in the limit where, I didn't explain what these are, but let's say in the surface diffusion there are atoms that are moving on each step, and they are jumping from one step to the other. So you are in the situation where the diffusion of moving in the step is much smaller than the rate of jumping. So this is called attachment-detachment limited kinetics. And and you get this equation here, which is by the same procedure exactly that I explained here. All right. So so this is the this part, and there is an interesting observation here. As I told you, the equations that you get are, for instance, for the going back to evaporation condensation. Well, actually, to both. You get this equation for F1, and then F2 would be satisfying this equation here. And then somehow we're interested to understand how propagation of curves will work in this case. And there is the following thing that you can observe. if you think that the 2-point correlation function is the product of the 1-point correlation function times some kind of function that describes how much correlation you have or how much decorrelation you have, if you want, and you use these equations here, you can compute the equation that lambda satisfies, and it's a transport equation. And because of the form of this equation and the interpretation because of the height, this equation is solvable. And actually, it turns out that lambda is a function of the heights, of the local heights, which I call to you that the local heights, they are related to f1 by the slope being minus f1. And this function here, you could compute in the sense that if I give you initial data, you can compute, let's say, what happens at t equal to 0, how much f2 correlates with respect to f1, and then you use this equation here to propagate this information inside the, for this problem. So, so this propagation of chaos would be included here if the initial data are, they are independent. That would mean that C is 1, and then it would stay 1 forever, of course. But somehow, it would allow you also to compute correlations, what they do at given correlation of the initial data. Okay, so there are some extensions here. For instance, random initial data can be done like that, and also Margetis has looked at what happens if you include also white noise to these equations, and you get diffusive terms that are added. And as I said, okay, this analysis is formal in the sense that there is a hypothesis in the background that the steps are distributed and do not aggregate as you approach the limit. Okay, and this, of course, in the diffusion problem, it will be the case. This is what you expect to happen. But there are problems in this area where the steps may aggregate. And this is when you have instabilities that are like having non-convex entropies, non-convex free energies. And it would correspond to the problem of step bunching. And in this case, of course, you cannot calculate the limit like that. It would be interesting to analyze such problems from the perspective of kinetic theory to see if one gets a handle for that. Okay. Let me go now to the issue of dilute polymeric liquids, and here it's I want a little bit to describe the models again and tell you a couple of things at the end. So this is a subject where it's a subject where you can have, as we heard here in the talk of de Villet, for instance, because somehow it's related, you can have microscopic descriptions, you can have mesoscopic descriptions, and you can have continuum descriptions. And continuum descriptions are the theory of viscoelasticity. This is the target continuum theory to compare. And okay, and there are various, there are big books. It's a very well-developed subject in chemical engineering literature. And the types of models that I'm interested in is problems where they are friction dominated. So somehow if you view them at the microscopic level, and let's say if these were point particles, they would be described by an equation of this form, where the frictional effects have been neglected. Fi would be the friction on each particle because of the underlying flow, and there is interaction through the flow. This term here would be, let's say, interactions between the particles. It would model interactions. For instance, you could think that you have certain structure between the particles, and you can introduce some kind of potential, like I did before. And then there would be Brownian motion in general. And somehow the issue would be to calculate what is the friction, and there are theories that do that well, that you can find in these books. but which are completely open in terms of mathematical analysis and of open problem. They lead to dynamics of stochastic systems, they lead to closure issues, to a lot of things that are to be explored, so to speak. So what I will do here, I will take the case where this relation is completely trivial, where each particle, let's say, only sees the surrounding flow as if it were alone. So this is the very, very dilute regime. And instead of looking, let's say, at point particles, I'm going to describe the Doi theory, where you have particles that look like rods, and they are embedded in a certain flow. And they interact with each other through the flow only. Okay. All right. So the equations that in order to this kind of particles, they need to be described by two variables, the position x and the orientation n. And they are friction theories. Okay. So they are of the type dx dt is equal to something. Now. And I'm interested in general in the case that you have also some applied force, which because these particles, they have different friction coefficient in the direction of the motion, in the direction of the particle in the vertical direction, you have to include a term like that to account for this. And you have to include also a diffusion that is a function of the orientation as well. Then there is the other variable, which is the variable n, which describes orientation. And here, this variable is moving with the flow, with a term that tells you that, well, kinematics, that if you have, let's say, some kind of flow that has a shear rate, grad xu, then this will cause a force that then, because you have that these are rigid rods, they can only rotate the particle. So this is the nature of this projection operator here. And there is rotational diffusion. Okay, and the coefficients of friction, they are different in different directions. And you take these equations here, and if everything is smooth, you do Ito calculus, and then you write the kinetic equation here, which is the kinetic equation. It has a transport term in x, well, a transport term in n, where n now will move on the sphere. Well, a Laplace-Beltrami operator on the sphere here because of the rotational diffusion, and a term because of the translational diffusion, and this term here is the transport because of the gradient of the field that is outside, let's say a gravity field. Okay, and then one needs to understand the interaction of the solvent and suspension, and the solvent to the rods is because of the imposed external flow that I already described. The main selection is the selection between the rods and the solvent, which is somehow the centerpiece of the Doi theory, how you select this. And it's selected by this type of formula here. So, there is a free energy into this problem, and it's given by this formula. So let me explain the following slide. There is a free energy to this type of problems, which is okay, entropy, actually minus entropy, plus internal energy, and the polymeric stress is selected like that, which in this case it looks like a second moment for the problem. And if you do that, then you obtain this kind of equation for the free energy. Okay, and this equation is okay. Of course, it is the reason that has attracted a lot of attention from mathematics. But this equation was because you have entropy and entropy dissipation, or entropy production, energy, free energy, and free energy dissipation. But somehow the choice of sigma is such so that this relation holds. And this relation expresses the principle of virtual works between, let's say, the suspension and the flow. And if you add this relation to the corresponding relation that you would get if you introduce also the Navier-Stokes equation, for example, I recall that a viscoelastic fluid, let's say for this context, it would consist of a relation, a viscosity of the solvent plus a viscosity for the polymeric stress. And so this would be the total viscosity, and the polymeric stress for this model is computed by that. So if you take this relation and you calculate, you multiply by U and calculate what happens for the kinetic energy of the fluid, you will get precisely a term that will offset this term, and you will get a decay, well, of the total energy, which will be 1/2 U square plus this term here, with this being the entropy dissipation. Okay. So let me say something about that. Let me actually bypass this part and go to go to understand a little bit. Well, okay, this problem is a problem of suspension of rods in solvents under gravity, which is a problem that we are interested now in studying, and this is the problem what I showed to you before, but where we have introduced some non-dimensional constants, where gamma would be the elastic forces over buoyancy, and delta would be the effect of buoyancy over the viscous force of the solvent. Let's say, so that I throw away all the numbers and we are left with these ones only. So we have this kinetic equation, and we have, you know, you can couple it with Stokes or Navier-Stokes, and I'm going to look at Stokes from now on. And I want to discuss a little bit the hydrodynamic limits of these problems, because somehow what happens is, if you have a suspension of rods, then if the rods are heavier, you are going to get an instability, and we were interested to understand what are the equations that describe, let's say, the long time dynamics of that. That was the reason for this exercise. So, so if you look at the hyperbolic limit in this problem, let me see, yeah, okay, then which means that you look at scales, x is 1 over delta x and t is 1 over delta t, and you compute, you get that you get a Boussinesq system in this, where this is some kind of average velocity, and then we wanted to see what happens if you try to look at the diffusive limit. Of course, in order to look at the diffusive limit, it has to be that the hyperbolic limit is trivial. And it happens that it's trivial if you consider a rectilinear vertical flow, which is of this type, where f also depends on n. Okay, I have forgotten this dependence here. And if it is a rectilinear vertical flow, there is no y dependence on v, and you have only the v variable, so this transport term drops out. And then we are going to look at, we are going to rescale and factor that out, and we are going to look at the diffusive limit. And if you do that, and you look at this scale, then you get a Keller-Sigel system of this form, which is Well, it's not surprising because of course, this being a mechanical theory will be isotropic, and since it is isotropic, that's the isotropic system that does the job. But what is a little bit more interesting maybe is let me tell you another way that you can view this problem. Here I have scaled space and time. Another thing that one can do is well, let's consider something that is simpler, like well, two-dimensional flow instead of three-dimensional like the previous one. And then in this case, you get the system here, if you compute. And what we do is an alternative that you can do is you can calculate second moments, which in this case is very simple, because these are the 2 second moments, and throw away anything that is more than second moment. The base for that is that because you have this term here, the higher the moment, you expect that there is more decay. Okay, then you get this system, and actually this system looks very much like systems that you obtain from Oldroyd type of fluids in continuum viscoelasticity. So that's one of the interests in these problems. And then you can say, all right, what happens if I do the following approximation, that I throw away the dTc and dTs term, and I stabilize these 2 equations, and I look at this as the equation for the dynamics. The reason that you can do that is that you have relaxation in this problem, and you can expect that the higher modes relax faster than the slower ones, which is the basis of this. And if you do that, you get this equation here. You can compute what is S, and you get a modified version of the Keller-Siegel model, where instead of having, let's say now that the speed is increasing, you have this term that saturates things. And this is something that somehow was familiar to me because from very long ago past work in the theory of viscoelasticity, we had this kind of phenomena that was associated with phase transitions in shear. In any case, that's the kind of model that you can get, and actually this one numerically is a better approximation of the problem. Okay, and this is what we're looking now, so I wanted to tell you a little bit of that. I know that there is an interest in biological derivations of such things, and this is a physics derivation of that. Okay, thank you very much.